Have you ever wondered how you can hear a clap of thunder from miles away, or maybe the faint sound of music from way down the street? Well, it all comes down to the invisible but super powerful science of waves. And today, we're going to break down exactly what sound is and how it gets from out there all the way to your ears.
And to really get our heads around this, we're going to tackle one of the most famous questions from all of science fiction. You've heard it, right? In space, no one can hear you scream. But is that actually true? By the time we're done here, you will know the definitive answer and, more importantly, all the cool physics behind it.
All right, so here's our game plan. We're going to start with the absolute basics, what a wave even is. Then we'll get into the two main types, connect that directly to what sound is, figure out how it travels, and finally we'll explore this incredible world of sound that we can't even hear. It's going to be fun.
Okay, let's kick it off with part one. What exactly is a wave? Well, it really all boils down to one thing: transferring energy. See, before we can even begin to talk about sound, we have to get a handle on this, because at its very heart, sound is a wave.
So here's the key idea, the most important thing to remember. Wave motion is all about moving energy, not stuff, not matter. You can think of it like a disturbance, a little jiggle that travels through something, but the something itself doesn't actually travel along with it.
And the absolute best way to picture this? Just think about dropping a stone into a perfectly still pond. You see those ripples, right? Those waves spreading out from where the stone hit? That isn't water moving from the middle to the edge. That's the energy from the stone's impact traveling across the water's surface.
Now, let's take it a step further. Imagine you toss a little cork into that water. What does it do? It doesn't ride the wave all the way to the shore. No way. It just bobs up and down in pretty much the same spot. This is the perfect proof of that main idea. The energy moves forward, but the water molecules, they mostly stay put, just passing that energy along to their neighbors.
Okay, part two flavors of waves, or as I like to call it, the slinky versus the rope. Now that we know a wave is just moving energy, it turns out there are a couple of different ways it can happen.
So first up, we've got what's called a transverse wave. The best way to think about this is to picture shaking a long rope tied to a wall. The wave itself travels forward, right, down the rope, but each little bit of the rope is just moving up and down. That up and down motion is perpendicular at a right angle to the forward direction of the energy. We call those high points crests and the low points troughs.
And the other type, it's a longitudinal wave. Now, instead of a rope, think of a slinky. If you push one end of the slinky forward, you see this little bunch of coils travel all the way down its length. In this case, the coils are moving back and forth, which is parallel to the direction the energy is traveling. Those bunched up spots are called compressions, and the stretched out parts are called rarefactions.
So let's put them side by side. Transverse wave, particles wiggle at right angles, making crests and troughs, just like on a rope. Longitudinal wave, particles push back and forth in the same direction as the energy, creating those compressions and rarefactions. And here it is, the big reveal for this section: sound waves are longitudinal waves.
Which brings us to part three, the nature of sound. Let's connect these waves to what we actually hear. Okay, so we've nailed down that sound is a longitudinal wave, but what actually starts that wave? Where does the sound even come from?
You know, the answer is actually really simple. It's vibration. Every single sound in the universe starts with something vibrating. When you pluck a guitar string, you see it vibrate. When you hit a drum, the surface vibrates. When you talk, your vocal cords are vibrating. That physical shaking is what kicks everything off. It pushes on the air particles around it and creates the sound wave.
And that brings us to the kind of fancy scientific definition of sound. But look, it just pulls together everything we've talked about. Sound is a longitudinal wave. Check. It's made by a vibrating body. Check. And this last part is absolutely crucial. It requires a material medium to travel through.
So how do we know for sure it needs a medium? Well, this classic experiment, the bell jar experiment, proves it perfectly. You stick a ringing bell inside a sealed glass jar, and then you start pumping all the air out. And as the air gets thinner and thinner, the sound of the bell gets fainter and fainter until it's completely gone. You can still see it ringing, but you hear nothing. No air means no particles to vibrate, which means no sound.
And that right there is the answer to our big question. Sound needs a medium. The vacuum of space? Well, it's a vacuum. There's no medium, no air, no particles to carry those vibrations. So, can anyone hear you scream in space? Absolutely not. It's not just a cool movie tagline, it's a fundamental rule of physics.
So, moving on to part 4, how sound travels. We've established that sound needs a medium, but does the type of medium make a difference? Oh yeah, it absolutely does. The medium is basically the rule book for how fast sound can go.
And just look at the massive difference here. In air, sound kind of plods along at about 330 meters per second. But in water, that jumps up to over 1,400. And in solids like steel, it's a whole different ballgame. Why? It's all about density. The particles in solids are packed super tightly together, so they can pass that vibrational energy to each other way more efficiently. I mean, look at that, a staggering 6,000 meters per second in something dense like granite. And this explains a really cool old trick. It's why you can hear an approaching train by putting your ear to the steel rail long before you can hear it through the air. The sound is just rocketing through that solid rail more than 15 times faster.
This also explains something we've all experienced, why you always see lightning before you hear the thunder. The lightning flash creates both light and sound at the exact same time, but light travels at an unbelievable 300 million meters per second. It basically gets to you instantly. Sound, though, it's chugging along through the air at just 330 meters per second, so it takes a little longer to arrive.
And that brings us to our last section, part 5, beyond our hearing. So we know what sound is, and we know how it travels, but here's a mind bender for you. Our own perception of sound is actually pretty limited. The full spectrum of what's out there is way bigger than what our ears can pick up.
So we measure sound frequency in something called hertz, which is just a fancy way of saying vibrations per second. For humans, the sweet spot, our audible range, is from about 20 to 20,000 hertz. Anything below that is called infrasound, these super low rumbles that animals like elephants and whales use to talk over huge distances. And anything above our range, that's ultrasound, the super high-pitched sounds used by bats and dolphins to see in the dark.
And this chart, wow, it really puts our own hearing into perspective. See that little bar for humans? Now compare that to a bat, which can hear all the way up to 100,000 hertz, or a dolphin, which goes up to 150,000. We are really only hearing a tiny, tiny slice of the acoustic world that's all around us.
But just because we can't hear these frequencies doesn't mean we can't use them. We've figured out how to harness ultrasound for some amazing technology, like the sonograms that let doctors see inside the human body, or sonar systems that let us map the deepest parts of the ocean floor.
So let's just end on this thought. We know sound is just vibration, moving through stuff, but our ability to actually perceive it is just one little window. It really makes you wonder, doesn't it? What kinds of conversations are happening right now? Between whales deep in the ocean or bats in the night sky, completely unheard, just outside the range of our ears.